everybody. Today we're going to take a look at some basics of organic chemistry. And if you talked about chemistry in the beginning of your chemistry class, like we did, chances are on either the first or the second day you talked about one of the branches of chemistry being organic chemistry. And if memory serves, hopefully you remember that organic chemistry was the chemistry of carbon-containing compounds. So when we think carbon-containing compounds, think again, carbon is the element of life. So a lot of these molecules wind up being things that are biological in nature and that we find inside of living things. There are a couple of exceptions that do go with organic chemistry where we do find carbon, but we don't necessarily label them as organic. And such things are carbon oxides, carbonates, and carbides. When you find those as part of the name of a chemical, those unfortunately are not going to be lumped under the umbrella of organic chem. Instead, they will be more of an inorganic chemistry type of topic. So let's go ahead and move on and look at some basics. Okay, so why is carbon so special? So carbon, of course, if you have a whole branch of chemistry named after you, you're going to have some unique characteristics to you. One of the characteristics of carbon is its ability to bond up to 4 things. So of course with this picture here, it comes from a great video on NPR called It's All About Carbon. You see that this carbon atom has 4 hands, and each of the hands is available to bond any number of things with it. If a certain other partner needs an electron, carbon has one to give 4 times. So it can bond 4 different things, or it can bond 4 of the same thing, which leads to a huge diversity of compounds that carbon can actually create. Another thing that carbon can do is it can bond with itself. So it can bond just 2 of them together, or it can bond 200 of them together. Carbon is an element that likes to bond to itself, and it likes to put itself in chains as well. When that happens, there's a special word for it. We call it catenation. That's a good vocab word. And lastly, let's just mention that carbon can form complex, branch, chain, ring, and even cage-like structures. So over here, you can see there's some definite unique substances that carbon forms. Many of you guys right now in your hand hold this chemical, graphite. It's carbon bonded to 2 other carbons for a C3 formula. But you add 1 more carbon into it and you change the way it bonds a little bit and you have C4, and now you have diamond's formula. So something as cheap as a pencil that has a lot of graphite in it compared to one of this Earth's most valuable substances, which is diamond, is only 1 carbon atom away in the structure. We also have these unique structures here. This is a buckyball. We see fullerene. We also have these things that are made of carbon called nanotubes, which is a substance of the future. And as we learn more about these nanotubes and their incredible strength, you'll see more and more things technologically that are going to be composed of nanotubes, including artificial human parts, coming soon. Okay, so hydrocarbons are going to be the simplest group of organic chemicals because they just have 2 elements in them. They have hydrogen in them and they have carbon in them, and that's where the name hydrocarbon comes from. Very easy stuff. Now, although it's just 2 very simple elements that comprise a hydrocarbon, since so many can bond to each other, the structures can be very large and very diverse, and in fact we know thousands of them that exist. The simplest unbranched or straight chain hydrocarbon molecules, these are going to be called alkanes, and these are the ones that we're going to look at the most today. We consider them saturated if each carbon atom forms 4 single covalent bonds. So what we can do is we can take a look at these molecules over here, and you can see that each of the carbons in the center has 1, 2, 3, 4 things bonded to it. As well, the one sitting right next to it, this carbon right here, has 1, 2, 3, 4 things bonded to it. And that makes this saturated. If you look at all the carbons in this line here, each one has exactly 4 things bonded to it, which is completely normal for carbon. Now, where we usually hear the term saturated and unsaturated is when we talk about fats in biology. And we say that some fats are saturated fats and some are unsaturated. Does that have anything to do with this? Actually, it does. So saturated fats have very long chain molecules. Here we see 5, but imagine, say, 15 more in this chain, which would be all the way over here somewhere. If every single one of those carbons is bonded to 4 things, and those hydrogens just keep on down the line here, and they wrap around and they go all the way back. That would be a saturated fat. That's the type of fat that we find as a solid fat, and we typically see that in the white parts of animal meat. That is a solid fat, or lard is a solid fat. Unsaturated fats are a little bit different. In their carbon chain, if you have a lot of carbons in a row, you're going to find that somewhere along the chain you're going to have a double bond instead of all the single bonds that we come to expect. And what that means is that these will not be bonded to 4 things anymore, because if you look at this carbon as is right here, you can see that it's already bonded to 3 things. You have 3 single bonds there, so all that's left is another possible one possible H to make its 4 bonds. Same thing with this carbon, 1, 2, 3, 4, and that makes this unsaturated. Now, where do you find unsaturated fats in living things? Well, you find them in plants. Maybe you've heard of the health benefits to fish oil and plant oils, or anything that doesn't make up a solid fat is likely to be better for you in terms of health than a saturated fat. We can also compress nuts and extract the oils that are present in things like walnuts and almonds and all those good nuts that you hear about that can benefit your health and your cardiovascular health. All right, so that is what a saturated hydrocarbon is. Let's go ahead and move on. Oh, one last thing I want to add there is that all bonds within your hydrocarbon are going to be single bonds. You're not going to find any double bonds if it's a saturated hydrocarbon. An unsaturated one you would. Okay, the first group, the alkane group, are your simplest hydrocarbon molecules. Each molecule will differ from the next in a series by a C and 2 H's. When that occurs, we call it a homologous series. So every one of these molecules is going to look similar, but it will be different from the next one in the line by 1 carbon and 2 H's. Let me show you what that looks like. So over here in this little table, you can see we have formulas for the first 10, and this one CH4 here, we have 1 C and 4 H's. In the second one, we have 2 C's and 6 H's. So what's the difference from one to the next? Well, it's a single C and 2 more H's. And if we go to the next one, of course, C3H8, there's an additional C and 2 more H's, C4H10, C5H12. As you go down, the same pattern exists. So the constant unit this one differs from is 1 carbon and 2 hydrogens. And that's simply shown down here in this general formula, where N equals the number of carbons. So if I throw up 6 in here, C6, the hydrogens, the number of hydrogens I'll have will be 2 times 6, which is 12, plus 2 is 14. So that would qualify for an alkane called hexane, C6H14. That's all there's to it. The first 3 alkanes we'll look at are pretty simple in nature, and the first one, methane, here you can see it has 1 carbon and it has 4 H's around it. Now this is what the molecule looks like flat on paper. This is a 3-dimensional view of the molecule, and you have to remember, in reality, this is how molecules exist. They're not flat on paper in 2 dimensions. Instead, they're 3-dimensional. They have a front, a back, a right, a left, and they have all sides associated with them. Now, where does something like methane come from? Well, it comes from underground. It was formed with coal, and now there's natural pockets of gas that exist inside the crust of the earth. And we go ahead and we extract that natural gas out and we burn it as a fuel. Now, a lot of people like natural gas because it puts out less CO2 than coal and burning oil. There are some issues that go with it, which I'll mention in a second, but because they were formed with coal during the mining process, there were some important safety precautions to take. Because methane is colorless and odorless, but it is poisonous, if you got trapped in a shaft, in a mining shaft, and you were breathing in pure methane, you'd suffocate. So if you've ever heard of the phrase, a canary in a coal mine, where that comes from is the fact that miners, being unable to see a completely invisible but toxic gas, they needed something, and their high-tech something was putting a canary inside of a bird cage, walking it down into a shaft and hanging it there. And what they would do when they went to work the next day is they'd shine a flashlight down the shaft, they'd see if the canary was still alive or not. And if the canary was not alive, it may signify that there was a gas leak. And because of the canary's metabolism is so fast, they breathed it in quickly and they, fell over in the cage and died. And that would be a sign to the miner not to go down there because you have a potential gas leak. Today's canary in the coal mine isn't even a coal mine at all. Today's species as our canary is the polar bear. And the reason why it's a polar bear, which is much different than canary, is because the polar bear is giving us information about our climate. As our Arctic ice caps are no longer there like they were in the past, as they are melting, the polar bear will likely be the first species to go extinct due to human-induced climate change. If there's no ice for a polar bear to hunt on, it's going to be impossible for a polar bear to get the amount of food that it will need to survive and give to its baby cubs to have them survive and continue with the species. It's very hard for a polar bear to exist on land when it's the color white. So over time it has evolved the white coat in order to be a more efficient hunter in the niche in which it lives. So when the polar bear finally does go extinct, we will know at that point we have a serious problem on our hands. Sometimes it takes something extremely shocking to be lost for people to wake up, and that may be it. As far as it being the canary, of course, that's linked to the greenhouse gas. Methane is a very potent greenhouse gas. It's number 2 after carbon dioxide. So in the case of this greenhouse gas, unfortunately, it is livestock that actually produce a lot of this methane, and you can imagine which end it comes out of. If you feed livestock the wrong food to get them fatter faster and bring them to slaughter, they're going to release a lot of byproduct of methane as they're feeding because it's not what they normally eat. For example, with cows and cattle and beef, we feed them corn instead of what they should be eating, which is grass. And when you give them corn, of course they're going to eat it. It's what you're giving them. They're going to release a lot of methane as a byproduct because it's not normal. It's not a normal part of their diet, but it does make them fatter faster. So that's a little background on methane. Let's take a look at ethane next. Ethane is a byproduct of petroleum distillation. So the black oil that comes out of the ground, when we distill it, we can break it into smaller pieces. So originally the carbon chain is very long, but as you break it into pieces, some of the pieces you get are 2 carbon pieces called ethane. And ethane is used for refrigerants and production of ethylene, which is a gas used in industry. Propane, which we all know because a lot of our grills on our back patios have propane tanks underneath them. We use them for cooking, we use them for heating, and those are also a byproduct of petroleum distillation. So as we distill that black oil, one of the smaller chunks might be this 3 carbon propane molecule. Okay, let's move on. When you get to the 4th alkane, which is butane, you will also come to the idea of an isomer. The isomer is the 3rd I word of our year together. We saw ion, we saw isotope, and now we have isomer. Isomers are compounds with the same molecular formulas but different structures, and their properties will vary if their structure is different. So with butane, for example, if you were to go ahead and take a look at the formula for this, it is C4H10. Here's 1, 2, 3, 4 carbons, so that's C4, and I have 4 and 4, that's 8, 9, 10. So I have C4H10. But if I look at isobutane, 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Identical formulas, but the structures are different. These are structural isomers of each other that have the same formula. A structural formula, where you kind of lay out in 2 dimensions what your molecule looks like, show the number and types of atoms in a molecule. So I can clearly see, because I just counted, the number of carbons, the number of hydrogens, and the types of atoms, carbon and hydrogen. They also show the arrangement, roughly. Okay, remember this is 2 dimensions, so I know that there's 3 carbons in a row, and off the 2nd carbon I have another carbon sticking off of this middle one, and it has its own set of hydrogens. So a little bit about the arrangement of the bonds, but it's not completely 3-dimensional yet. You can, once you have a little bit of chemistry in your background, you can figure out what the bond angles are, but for now let's just say this 2D is a representation of the arrangement of the bonds. Down in the corner here, you also see a couple of different ways to write the formulas besides C4H10, and we call those structural, condensed structural formulas because it gives a little bit more detail here. Instead of saying C4H10, we say CH3, CH2, CH2, CH3. Well, what they're talking about is this. This right here is CH3, this is CH2, this is CH2, and this is CH3. So it gives you a little bit more information than just C4H10. It gives you an idea of how the molecule will play out. Okay, this one here would be shown a little bit differently in terms of its condensed structural formula. Do you know your polygon prefixes? If this is your 10th grade chem class, you've also had geometry this year, which means that your polygon prefixes are going to play a part in you knowing how to name these alkanes. Hopefully you've seen that the 4 we've covered so far, methane, ethane, propane, and butane, all seem to have that A and E ending. Now the front of the word, however, goes with your geometric prefixes you learned when you were in geometry. For example, pent meant the number 5, hex was 6, hept is 7, and oct was 8. And if you count the numbers here, sure enough, you'll get 8, 7, 6, and 5. All right. Each one of these is also formed from petroleum distillation. We thermally crack oil and break them into smaller chunks. This one here winds up as a portion of your gasoline that goes in your car. So when you go to the gas pump and you see the 3 numbers there, 87, 91, 93, they're talking about how much of this molecule right here makes up the gasoline fuel that you're pumping into your car. Additionally, what we can say is that if you have more carbons, we just saw butane with an isomer. But once you get 5, 6, 7, 8, the number of isomers starts going up dramatically. So the more possibilities that you can fold this thing into, the more isomers you're going to have. Let me show you an example with octane. I have 8 carbons here. So what are the isomers of octane like? Well, here you go. You have 18 different ways to connect 8 carbons and 18 hydrogens, and they all have different names. They all have different properties, boiling points, freezing points, densities. It's all different. They're all different chemicals, even though they have the same formula. Okay, and that's the beauty of an isomer. Okay, the last 2 alkanes as you go from 1 to 10, of course, are nonane, C9H20, and you have decane, C10H22. If you weren't real sure on how these things connect, remember there's a shared pair of electrons when you covalently bond with anything, and here they all are. So that is a lot of single covalent bonds. Okay, there's also a group called the cycloalkanes, which are unique because it is your alkanes that have folded back upon themselves, and from their folding back upon themselves, they form ring-like structures. So if we take a look at these 3 right here, you can see that each one has one of its alkanes at its heart, but that alkane is folded back upon itself and reconnected to the other end. So I know this is butane because it's 1, 2, 3, 4 carbons. Okay, I know it's cyclo because it is folded back upon itself and reconnected. This one here would be pentane. 1, 2, 3, 4, and 5 carbons. And this one here is hexane as well. Now, it is understood that there's a carbon atom at each corner, which you can clearly see in these 3 examples, and enough H's to complete the 4 bonds a carbon atom requires. So in the case of this here, let's look at this carbon and focus on this one right here. You can see 2 of the bonds present already. This carbon needs to bond to another carbon here and here. That takes up 2 of the 4 bonds carbon will make. But you also see 2 hydrogens attached to this carbon. So it's likely that they're going to be sticking off like this. And that makes 1, 2, 3, 4 places that will bond to a single carbon. And that's what's necessary in these alkane molecules. Now, sometimes you'll get it drawn like this, but sometimes you'll get an abbreviated version because it takes a lot more space to write them like this than like this. This right here is the typical way you'll see them in an organic book. The way they draw them here is in confidence that you, the student, will understand that there is a carbon at each corner. This is cyclobutane we just saw before. But you're also supposed to understand that not only is there a carbon, but there's enough hydrogens there in order to make a total of 4 bonds around each of the carbons. So there's going to be 2 here, 2 here, 2 here, and 2 here as well. And you should be able to do that with any of these, all the way from cyclopropane up to cyclododecane. Okay, for each little tiny angle here, each corner, you're going to have a carbon, and you're going to have enough hydrogens in order to make 4 bonds. The formula for a cycloalkane is a little bit different because it folded back upon itself. We have C, N is the number of carbons, and we have H times 2, we have H where it's 2 times N, 2 times the number of carbon gives you the number of H's that you have. Now, we don't need, if you remember butane, it was like this. It was CH3, CH2, CH2, CH3. And what it looked like was 4 carbons in a row, and the 2 N's had 3 hydrogens around them. Now, if those ends fold back upon themselves, you're going to remove 2 of the hydrogens in order to do that. So what's left over then, if I go ahead and fill out the rest of this here, let me put in all my single bonds. There, now I have C4H8, which makes a lot more sense for cyclobutane. So in this case here, we subtract a couple of hydrogens off, and that gives us the formula for cycloalkanes. All right. Another unique thing that you see with organic is these snake-like structures here, these line drawings. And again, at every corner, there exists a carbon atom, also at each end. So if I look at something like pentane, for example, I have a C here. I have a C here, a C here, a C here, and a C here. So even though it's not explicitly showing it, I know they're there. And I also know there's enough carbons around this to make sure that there's 4 bonds to each of these molecules. Okay, so I have 1, 2, 3, 4. And that's, sorry, it's an H. It looks kind of sloppy. And I know that this one here, because it's bonded to 1, 2 carbons, there's only room for 2 more hydrogens. So a couple of hydrogens there. Same thing for this one here. Same thing for this one here. But this one here on the end only has 1 bond to a carbon. So now I have 1, 2, 3 more hydrogen bonds. And that's where I get C5H12. If you count up all this stuff in here, I know it's a little bit messy, but you can definitely tell there's 5 C's and 12 H's in that molecule. So how do we go about naming these things? Well, with alkanes, it's really easy, and we've already gone through a bunch of them here. So the most important thing to remember is that ane makes up the ending, and if you took geometry, you're already familiar with all of these prefixes down here. They go in front of the ane. So let's just test ourselves real quick. This molecule right here, if you had to make a guess, go ahead and guess right now. Just count your carbons. 1, 2, 3, 4, 5. That makes pentane. All right. Majority of molecules, though, are not just straight chain alkanes. They have branches stuck to them. And these branches, the ones that we're going to look at, have branches made of alkanes, or we'll say alkyl groups, because they were alkanes, but they lost a hydrogen. So imagine a branch on a tree. You know, you have the major branch, which we're going to call the parent branch, and then you have a whole bunch of twigs sticking off of that. Those are going to be our alkyl groups, and they're going to be connected to that parent chain or that parent branch. And the alkyl groups, again, come from an alkane that has lost an H. And when you name them, you're going to remove that ane. Instead, you're going to add YL. So let's take a look at methane. Methane is your simplest alkane. It's CH4. Looks like that. But if I remove one of the H's, what's left over is this. Okay? So I have CH3. And we go from methane to a methyl alkyl group, which can now connect onto something. If you want to, think of this like a stem that can stick to something. If I have the hydrocarbon alkane that has 2 carbons right here, hopefully you know its name is ethane. But if one of those H's is removed, and what's left over then, and for variety's sake, I'll go ahead and I'll remove one from the other end. There. This H is now gone. It's no more. And now I have a little stem sticking off of it, which can connect onto a parent chain. So this would not be ethane at this point. This would be an ethyl alkyl group, which can now connect onto another alkane. Okay, so let's take a look at a molecule, because I think that's the best way of learning how to name something. And our first step, as you can see here, to name it, locate the parent hydrocarbon. It is the longest chain, and additionally, it may be bent. So what we can do then is we can take a look and we can act like detectives and figure out what is the longest possible carbon chain you can find in this thing. And if I go ahead and I start here, I have 1, 2, 3, 4, 5. So that one's 5 long. I can also see 1, 2, 3, 4, 5 equal. 1, 2, 3, 4, 5 also equal. So in this case, 5 is definitely the longest chain that I have. So for sure, I have pentane as a parent hydrocarbon or parent alkane. Step number 2, identify and name alkyl groups, alphabetize in front of the parent chain's name. So again, my parent chain was pentane. I'm going to write that over here. And now I'm going to go searching for alkyl groups. And let's just stay real basic. Let's say this bottom one right here. This is going to be our parent chain. And my alkyl groups that I've attached to it, I got one right here, which is CH3CH2. We just saw it on our last slide. And I also have this one sticking off of it, which comes from methane. So this is a methyl group right here. And this is an ethyl group right here. Okay, it came from ethane. So it says identify and name alkyl groups, alphabetize in front of parent chain's name. So ethyl comes before methyl alphabetically. So I'm going to have ethyl. I'm going to put methyl pentane. Ethyl methyl pentane. If multiple alkyl groups, then attach appropriate numerical prefix. Now, and I should put in here if multiple same alkyl groups. Like if I found that there was a methyl on this one, a methyl on this one, a methyl on this one, I would use a prefix that would represent 3 methyls, which would be trimethyl. But I don't have that here. I have one ethyl and I have one methyl, so I don't need to do that in this case. Next, number my parent chain so that the alkyl groups have the lowest possible numbers. All right, so I said it was the bottom line. What if I go like this? 1, 2, 3, 4, 5. In this case, my ethyl group is at carbon number 3, and my methyl group's at carbon number 4. The problem with this is it doesn't number them so that my alkyl groups have the lowest possible numbers. Instead, because they're at the 3 and 4 position, what if I flipped that around and instead of doing that, I numbered the other way from right to left? Then I would have 1, 2, 3, 4, and 5 carbons. And here, my methyl is off of a 2, which is a lower number than it would have been a second ago. A second ago, I had 3 and 4. Now I have my alkyl groups on carbon number 2 and carbon number 3. So this would be the right formula, the right numbering system to use. Place the location numbers of each of the alkyl groups in front of its name. Separate with a hyphen. So in the case of my ethyl group, I found it at position 3. So I'm going to have 3 ethyl. And my methyl group, which is right here, is on my carbon number 2. So it would be 2 methyl pentane. Okay. The last thing, separate numbers with commas if necessary. And if you'd like, we can either put a hyphen in here. And in fact, let's do that. Let's put a hyphen in there. When they say separate numbers with commas, if we had like 2 of the same alkyl group on different carbons, we could say like 2, 3, 4 methyl, or 2, 3, 4 trimethyl if there were 3 of them on carbon number 2, 3, and 4. We don't have that here, so for now let's just put a hyphen in between the two. So we have 3 ethyl, 2 methyl pentane. That would be the name of this particular branched chain alkane. Now, take a look at this thing. This looks like someone standing on their head, okay? But what this is actually organic molecule. And what we got to do is we got to make sense of this thing and figure out what its name is. So we have to be in the business of counting carbons. And remember, at every corner and at each end, you're going to have a carbon present. So if it helps you to draw them in, just make a little mini C around your structure. Every place you find a corner, every place you find an end, if that if that helps you, go for it. All right, let's find our longest chain. 1, 2, 3, 4, 5. So there's a 5 carbon. 1, 2, 3, 4, 5. There's another 5 carbon. And we just lost power here in our building. Hopefully the light will illuminate my face enough. And we have 1, 2, 3, 4, 5. There is another carbon as well. I'm going to go ahead and pause for a second. I'll be right back with you guys. Okay, we're back. Crisis averted. Power's back on the building. Okay, so every way you cut this one, it has 5 carbons in a row. And so that gives us a parent chain name. It's pentane once again. Of course, not every molecule is going to wind up as pentane, but in this case, our examples happen to be pentane. That's okay. All right, so what we have to do then is we have to figure out what alkyl groups we have connected to our 5 carbon chain. Okay, and in this one here, if I went ahead and I started numbering, there's a number of things I can do here in looking at this molecule. I saw the 5 going this way, but since I don't know right now with what we've covered of what a weird shaped addition this one would be, we see a carbon kind of like in a plus symbol. I'm not going to use that parent chain. Instead, I'm going to use this one here. I'm going to make this my carbon I'm using. I'll circle the ones I'm going to use. This one here, this one here, this one here, and this one here. Okay, I'm just going to use with the knowledge of what I've covered so far. And the alkyl groups then that I would see is, I know this one here would qualify as a methyl group because there is a carbon at the end, but we know there has to be enough hydrogens to make a total of 4 bonds. So there they are. So we have a methyl and another methyl here. So in this case, we have dimethyl going on. And I also have, coming off of this carbon here, a 2-carbon alkyl group. And of course, a 2-carbon alkyl group is called ethyl again. So what I wind up having then is an ethyl, and I have a methyl, dimethyl to be more specific, because there's 2 of them, pentane. Now, what I got to do then is I got to figure out how to number my compound. So I can either go 1, 2, 3, 4, 5, or I can go 1, 2, 3, 4, 5. Now, if you remember the rule, it was that our alkyl groups had the lowest possible number. So here I'd have a 3 and a 4 with my alkyl groups. But if I number up that way, then I have a 2 and a 3. And that sounds lower to me, so that's the one I'm going to use. So in the case here, I have 3 ethyl, and I have 2 dimethyl pentane. So it's kind of jammed up here. Let me write that a little bit nicer for you. 3 ethyl, 2 dimethyl pentane. There we go. It's a little bit nicer. If you haven't yet noticed, the precision on my little writing pad is not the best. So I do my best on these. Okay, so that is drawing a molecule. Let's see if we have anything else. Or I'm sorry, that was deciphering a molecule into the name. One more thing, let's try. Let's draw one. Let's see what happens. Let's have a 2-methyl, 2-ethyl butane molecule. I know butane is 4 carbons long, so that's going to be my first step, just drawing it out. I can go ahead and number it right off the bat because you're allowed to when you're drawing them. 2-methyl, 2-ethyl. So what that tells me is that coming off of carbon number 2, I have a methyl group and I have an ethyl group. So an ethyl group, again, is 2 carbons. Last thing I'm going to do, of course, is I'm going to fill in what's left over, which are the H's that are all missing. And I just got to make sure everything has 4 total. If your identity is a carbon, you got to have 4 things around you. So I'm just going to fill and fill and fill until I have 4 around everything. Okay. Here's a C that's getting filled up as we speak. So now this is going to be on paper 2-methyl 2-ethylbutane. If you take a look and you did a count, every single carbon has 4 things around it, which is absolutely necessary. This thing here winds up being my methyl group. This thing here is my ethyl group. These two are carbons in the butane chain. They have nothing to add, nothing to do with it whatsoever. And that is the finished structure. And it looks pretty awful right now, but you know, if you had a cleaned up version of it, you could draw it in a special way. You could go 1, 2, 3 like that, and that gets you a carbon here, 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 and here. And to show my methyl group, I could throw just one of those upward, and to show my ethyl group, I could go down here, and I could bend that there, and all of a sudden that somehow is this molecule here, which sounds crazy, but it's true. So I hope you understand the basics of organic. This takes a lot of reading, it takes a lot of imagination, using the right half of your brain, and you know, keep working. Do as many of these drawings, do as many where you get the drawing, you have to convert it to a name as possible. That's how you get better with organic chemistry. So keep studying, and I'll see you next time.